Welcome to the Unit 7, Section 2 video on radical expressions. Recall that squaring a number means multiplying that number by itself. So you have 8 squared is equal to 8 times 8, which is equal to 64. Negative 8 squared is equal to negative 8 times negative 8, which is also 64. The opposite of squaring a number is finding its square root. To find the square root of 64, you must find a number when multiplied by itself yields a product of 64. Since 8 times 8 is 64, 1 square root of 64 is 8. Since negative 8 times negative 8 is also 64, another square root of 64 is negative 8. There may be a situation where it makes sense to use one root over another. For example, if a problem involves finding length, you would use the positive root and not the negative, since you cannot have a negative value for length. And just a reminder that when we're talking about radicals, your index is the number inside the radical, or at least on the outside of the radical. If it's not present, it's understood to be 2, which is the square root. Inside the radical, you have the radicand, and then the symbol itself is the radical. So when you have a square root is a radical with an index of 2. A square root is simplified if the radicand has no perfect square factor other than 1. A perfect square is any number squared, or any number times itself. And here's a list of some of those perfect squares. 1, 4, 9, 16, 25, 36, 49, and so on. All of these are perfect squares. A cube root is a radical with an index of 3. A cube root is simplified if the radicand has no perfect cube factor other than 1. A perfect cube is any number cubed, or any number times itself twice over. So here's a list of some of your perfect cubes. And you can find these in your calculator, right? You can do 4 cubed is 64. You can do 5 cubed as 125. So you can figure out what perfect cubes are by using your calculator. So let's determine if each radical is simplified, starting with the square root of 7. Well, since we don't have but 2 perfect squares before it, we're going to throw 1 out because a 1 is a factor for everything. So we'll go on to 4. 4 does not divide evenly into 7. And then the next perfect square is 9. And 9 is bigger than 7, so we can stop there. It is simplified. For the cube root of 36, we have to consider what our perfect cubes are. 36 is a perfect square, but it is not a perfect cube. So this is simplified. Square root of 27. Well, does 27 have a factor that is a perfect cube? Well, 9 is perfect square. 9 is a perfect square, and 9 can divide evenly into 27. So it is not simplified because 9 is a factor of 27. 9 will divide evenly into 27. The cube root of 90. Well, you got to think about your perfect cubes. And since no perfect cube is a factor of 90, it is simplified. For the square root of 128, well, we know that 4 will go into 128. 16 will go into 128, so that's actually a perfect square that's bigger. So it is not simplified because if we continue on, 64 is actually the largest factor that's a perfect square. That is a factor of 128. But regardless, we know it's not simplified. For f, we have the cube root of 12x to the 6th. So it is not simplified because x to the 3rd is a factor of x to the 6th. A radical expression is in simplest form if the radicand has no perfect square factors other than 1. The product property of radicals can be used to simplify radical radical expressions. So for any numbers a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, the square root of ab is equal to the square root of a times the square root of b. The product property of radicals states that if you're multiplying two things inside the radical, you can split up the radical into two separate radicals, multiplying those elements. So instead of the square root of a times b, we can do the square root of a times the square root of b. So consider the square root of 27 from example 1. It was not simplified because 27 has a perfect square factor of 9. Using 9 times 3 equals 27, we can use the product property of radicals to simplify. Square root of 27 is equal to the square root of 9 times 3. Then we can split it up into the square root of 9 times the square root of 3, and the square root of 9 is 3. So we end up simplifying it to 3 times the square root of 3. So let's do some examples of this by simplifying each radical. So let's start with the square root of 12. We can split up the 12 in the square root as 4 times 3. 4 is a perfect square, so we can split it up as the square root of 4 times the square root of 3 and take the square root of 4, which gives us 2. So we simplify this to 2 times the square root of 3. For the cube root of 40, we need to find a perfect cube that goes into 40, and that would be 8. 8 times 5 is 40. The cube root of 8 is going to give us 2, so we have 2 cube root of 5. For C, we have 112x squared. We can split up the 112 into 16 times 7, and we also have an x squared. So since we can split all this up, since everything's being multiplied, square root of 16 gives us 4. X squared, when we take the square root of that, gives us x, and then we're left with a square root of 7 on the end. When we do the cube root of 256x to the 9th, we can split up 256 into 64 times 4, 64 being a perfect cube. Then we can split up all of our radicals, since everything's being multiplied. The cube root of 64 is 4. The cube root of x to the 9th is x to the 3rd. And then you have the cube root of 4 left over. Now I am going to make the suggestion that when you're dealing with a radical that has an index, to go ahead and put a multiplication dot in between so that we don't confuse the power that's right before it with the index that comes after it. For the next one, we have the square root of 72, x to the 9th. So we are going to split up the 72 into 36 times 2, since 36 is a perfect square. We're going to split up the x to the 9th into the x to the 8th and x, because 2 goes evenly into 8. And then we're going to split up all of our radicals. Square root of 36 is 6, and we're left with the square root of 2. Square root of x to the 8th is x to the 4th, and then we're left with the square root of x. And then we're going to combine our square root of 2 and our square root of x together on the end and have 6x to the 4th times the square root of 2x. For f, we have a cube root of 54x to the 7th. Find a perfect cube that goes into 54, and that would be 27. And then 3 goes evenly into 6, so we're going to split up our x to the 7th into x to the 6th times x. We're going to split up all of our radicals, and then take the radicals that will go evenly, which are your cube root of 27, which is 3, and our cube root of x to the 6th, which is x squared. Because 3 goes into 6 2 times, our index goes into our power under our radical evenly 2 times, so that gives us our new power. And then we're left with this when we rewrite it. You can divide radicals and simplify radical expressions that involve division by using the quotient property of radicals. For any numbers a and b, where a is greater than or equal to 0 and b is greater than 0, you can take a fraction underneath a radical symbol and split it into two radicals that are being divided by each other. For example, if we have the square root of 4/9, we can rewrite it as the square root of 4 over the square root of 9, which allows us to simplify the expression into 2/3. So let's do a few examples of this. The square root of 16 over 25. We're going to split this up into the square root of 16 over the square root of 25. And the square root of 16 is 4, and the square root of 25 is 5. For b, we've got the cube root of 216 over 27. We're going to split this into two radicals that are being divided by each other. The cube root of 216 is 6, the cube root of 27 is 3, and 6 divided by 3 gives us 2. For the next one, we are again going to take the square root of the top divided by the square root of the bottom. The square root of 121 is 11. Square root of x to the fourth is x squared. On the bottom, we have the square root of 36, which is 6, and the square root of x squared, which is x. And then we can simplify this further by canceling 1x off the top and the bottom. So this gives us 11x over 6. For d, we have the cube root of x to the 15th over 125. We're going to split it into a radical on the top and the bottom. The cube root of x to the 15th is x to the 5th. The cube root of 125 is 5. For e, we have the square root of 4 over 64x squared. We can simplify this by splitting up our radicals and dividing them by each other. Square root of 4 is 2. The square root of 64 is 8. The square root of x squared is x. So we have 2 over 8x. And of course, we can simplify that down to 1 over 4x. Next, we have the cube root of 1,000 over 125. Split it up. The cube root of 1,000 is 10. The cube root of 125 is 5. And 10 divided by 5 is 2. Adding radical expressions with the same index and the same radicand is just like adding like terms. We call radicals with the same index and the same radicand like radicals to remind us they work the same as like terms. We add and subtract like radicals in the same way we add and subtract like terms. We know that 3x plus 8x is 11x. Similarly, we can add 3 square root of x plus 8 square root of x, and the result is 11 square root of x. When you have like radicals, you just add or subtract the coefficients. When the radicals are not like, you cannot combine the terms. So let's simplify each expression if possible. Here we have 2 square root of 2 minus 7 square root of 2. If we were to collect our coefficients, we can do 2 minus 7, which would give us negative 5 square root of 2. For the next one, we have 5 cube root of y plus 4 cube root of y. Again, the cube root of y's are like terms, so we're going to collect our coefficients, and that gives us 9 cube root of y. For this example, we have a square root of x and a square root of y term. Those are not like terms, so since the indices are the same but the radicals are different, these are not like radicals. Since the radicals are not like, we cannot subtract them. For radicals to be like, they must have the same index and radicand. When radicands contain more than one variable, as long as all the variables and their exponents are identical, the radicands are the same. Very similar to how we did it earlier when we had, say, x squared y. As long as the exponents are the same on the same variables, then we have like terms. Remember that we always simplify radicals by removing the largest factor from the radicand, that is a power of the index. For square roots, we factor out the largest possible perfect square. For cube roots, we factor out the largest possible perfect cube. Once each radical is simplified, we can then decide if they are like radicals. So let's see if we can simplify these. we have 9 square root of 50m squared minus 6 square root of 48m squared. So let's simplify the radicals first. Our largest perfect square for 50 is 25. Our largest perfect square for 48 is 16. So we're going to factor out those items. And when we simplify the radicals, we get 9 times 5m square root of 2 minus 6 times 4m square root of 3. And that gives us 45m square root of 2 minus 24m square root of 3. And since our final radicals are not like, we cannot combine them. So this is as simple as we can write this expression. For b, we have two cube root terms. One's got a 54n to the fifth in it. The other has a 16n to the fifth term in it. The largest perfect cube that will go into 54 is 27. The largest perfect cube that will go into 16 is 8. And when we pull out those largest perfect cubes, this is what remains. We'll go ahead and simplify our cube root of 27 into the third. That's going to give us 3n. Our cube root of 8n to the third is 2n. And since the remaining radical on both of these terms is the cube root of 2n squared, we can combine these two like radicands and get n cube root of 2n squared. We have used the product property of radicals to simplify square and cube roots by removing the perfect square and the perfect cube factors. We can use the product property of radicals in reverse to multiply square roots. Remember, we assume all variables are greater than or equal to 0. When we multiply two radicals, they must have the same index. Once we multiply the radicals, we then look for factors that are a power of the index and simplify the radical whenever possible. Multiplying radicals with coefficients is much like multiplying variables with coefficients. To multiply 4x times 3y, we multiply the coefficients together and then the variables to give us the result 12xy. So let's do some examples of multiplying radicals together. Here we have 6 square root of 2 times 3 square root of 10. So we're going to multiply the coefficients. 6 times 3 gives us 18. And we're going to multiply the radicals. 2 times 10 gives us 20. So we have the square root of 20. The largest perfect square that goes into 20 is the square root of 4. And the square root of 4 gives us 2. And so 18 times 2 is 36. So we end up with 36 square root of 5. For b, we multiply the coefficients. Negative 5 times negative 4 gives us positive 20. We multiply 4 times 6 to get the cube root of 24. Then we find the largest perfect cube that goes into 24, which is 8. 8 times 3 gives us 24, so we split up our cube root. The cube root of 8 is 2, and 20 times 2 gives us 40. So our final answer is 40 cube root of 3. For this one, we have 10 times 4, which is 40. 6p to the third times 3p. 6 times 3 gives us 18. P to the third times p. We use our exponent rules, add the exponents, so we get p to the fourth. The largest perfect square that goes into 18 is 9. And the p to the fourth, we can take the square root of, so that's going to leave us with square root of 9p to the fourth, and then square root of 2 will be our leftover. We take the square root of 9p to the fourth, that gives us 3p squared, and then 40 times 3 gives us 120. So our final answer is 120p squared, square root of 2. For d, we're going to do 2 times 3, which gives us 6. 18 times 12 in the cube root gives us 216. And y to the fourth times y squared gives us y to the sixth. The largest perfect cube that goes into 216 is 36. And we can take the cube root of 6 of y to the sixth because 3 goes into 6 evenly. And we take our cube root of the things that are perfect cubes. and then multiply 6 times 6 to give us 36y squared times the cube root of 6. Expressions in simplest form cannot have roots in the denominator. You must rationalize any denominator that contains a radical. For denominators with a single radical, we multiply both the numerator and denominator by a radicand that creates a perfect square. So let's take a look at this using examples. We have the square root of 5 over 2, which we can break into the square root of 5 over the square root of 2. But our final answer cannot have a radical in the bottom. So we're going to multiply the top and the bottom by the square root of 2, which essentially is the same as multiplying by 1. We're not changing the value, we're just changing how it looks. So we multiply the top, we get the square root of 10. On the bottom, we end up with the square root of 4. And so the square root of 4 on the bottom becomes 2. So we have square root of 10 over 2. There are no radicals in the bottom, and so now we are simplified. For b, we have the square root of 6 over 5. We break up our radicals, and then we multiply the top and the bottom by the square root of 5, which gives us the square root of 30 over the square root of 25, and the bottom simplifies into 5. For the next one, we multiply the top and the bottom by the square root of 3, and that gives us the square root of 21 over the square root of 9, which gives us the square root of 21 over 3. For d, we have the square root of 1 over 6, which we can multiply the top and the bottom by the square root of 6, which gives us the square root of 6 over the square root of 36, and the bottom is a perfect square, so we have the square root of 6 over 6. For e, we have the square root of 9 over 8. So we can actually take the square root of 9 already and get 3. We can simplify the square root of 8 because it's the square root of 4 times 2, which gives us the 2 square root of 2 on the bottom, but we still have a radical in the bottom, so we have to get rid of it by multiplying the top and the bottom by the square root of 2, and so we end up with 3 square root of 2 over 4 once you finish simplifying the bottom. When we get into cube roots, we do a similar thing, but instead of rationalizing by multiplying the top and the bottom once, we have to do it twice. That way we end up with a perfect cube in the bottom. So here we have the cube root of 7 cubed, which gives us the cube root of 147 over 7. For example G, we have the cube root of 4 over 18. We're going to multiply the top and the bottom by the cube root of 18 squared, which is going to give us the cube root of 18 to the third in the bottom, and the cube root of 1,296 on the top. There is a perfect cube that goes into 1296, and that is 216. So we're able to simplify the top to 6 cube root of 6 over 18, which then gets reduced down to the cube root of 6 over 3. And now for h, we are going to multiply the top and the bottom by the cube root of 3 squared t squared. That is going to give us our perfect cube in the bottom of the cube root of 3 to the third, t to the third, which gives us 3t in the bottom. We can simplify the top because the perfect cube of 3 squared is going to be 18. Okay, so we actually we don't have a perfect cube. What we have is 2 times 3 squared, which is 2 times 9, which is 18. So we have the cube root of 18t squared on the top, and then 3t in the bottom. So to summarize, when simplifying radical expressions, you want to check the following conditions to determine if you have the expression in simplest form. A radical expression is in simplest form when these 3 conditions are met. No radicands can have perfect square factors other than 1. No radicands contain fractions, and no radicals appear in the denominator of a fraction. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.